Good evening, everybody. It's Thursday, the 26th of March, and this is Nighttime Mathematics Radio. Well, we're still living in this strange world where all the math classes have stopped, and the homework just keeps going on and on and on. I'll be on weeknights at 9 p.m. Pacific Time as long as that keeps happening. Now, we had a few questions come in between last night's show and tonight's, so I'll have a few things to talk about today, but just in case anybody's been waiting to ask a question, let's take 1 minute to see if anybody has a question on Twitter. This is Nighttime Mathematics Radio. Alright, welcome back, everybody. Let's take a look at the first question that came in over the weekend. This is a calculus question that came in from an AP Calc student, and it looks like this. This question says, we've got a graph of f of x that looks like this, and we've got a sort of a picture of it here. At -1, it starts on the axis, pops way up, then back down again where it hits the axis again at 2. Curves down, goes through a bit of a minimum at 3. Comes back up, crosses the axis at 6. Pops again up here. Goes through another little maximum, curls down, just touches at 10, then takes off, and ends at 11,1. They show the height here is 4. The distance down here is 3. I think those 3 is the distance down they show here. Distance up here is 2. And this is, as I say, 11,1. This point here is right at 10. They say the area is bounded by the graph of f of x and the x-axis on the intervals... Oh, it's, okay, these are the areas bounded, they say. The area is bounded by the graph of f of x on this interval is 4. So this is the height. This area here is 4. This area here is 3. This area here is 2. And they say the graph of f of x, the graph g of x, sorry, the function g of x, I should say, is defined on -1 to 11. And g of x is given by, g of x is the integral from 2 to x, f of t dt. For any x in -1 less or equal to x less or equal to 11. And then just to have one more function flying around, we're also given an h of x. That's given by a piecewise definition. It's x squared plus 3x minus 2 for x less than minus 1. And then it's g of x again. That g of x we just defined for minus 1 less or equal to x. Minus 1 between x, less or equal to x, less or equal to 11. Okay, so what are we asked to do? First question is, show that h of x is continuous at minus 1. I should say this is defined, this is this for x less than minus 1. Oh yeah, I said that before. Never mind. Okay, there we are. Oops. Oof. Obviously you need a bit of sleep tonight. So show h of x is continuous at x equals minus 1. Well, what has to happen for a piecewise function like this to be continuous? Three things. 1, h of minus 1 must exist. 2, the limit as x approaches minus 1 from the left must exist. And b, h of minus 1. And third, the limit as x approaches minus 1 to the right must exist. And b, h of minus 1. So the function must have a limit to the left, it must have a limit to the right, it must exist at the point, and all three have to agree. Now, two of these are really obvious. First of all, h of minus 1 certainly must exist. Why? Because, well, we have a definition of it right here, and g of x is just the integral of a continuous function. It's obvious that f is continuous. You can see it. It's drawn there. So what is that? What is the integral from... what's g of minus 1? Because after all, we know h of minus 1, by definition, is g of minus 1. Well, that must be the integral from 2 to minus 1 of f of t dt. Well, that looks sort of backwards, and it is, because you notice that this interval is upside down. The bigger values on the bottom, the smaller values on the top, and that's fine. Remember there's a definition of that. When you integrate backwards like that, you just count all the areas negative. So that's minus the integral from minus 1 to 2 f of t dt. How do we find that? Well, it's labeled. That's literally the area under this curve. It's 4. So that's equal to negative 4. So fantastic. That's equal to minus 4. And because we know the integral of a continuous function is continuous, that's also the limit from the right. So the limit as x approaches minus 1 from the right of h of x is also equal to minus 4 because g of x is continuous. So the last question is, what's the limit from the left? Well, the definition on the left is also a continuous function. This definition, this x squared plus 3x minus 2, is continuous. So the limit as x approaches minus 1 from the left of h of x is just the limit as x approaches minus 1 to the left of x squared plus 3x minus 2. And because that's a continuous function, you can just plug in minus 1 and see what you get. So that's equal to minus 1 squared plus 3 times minus 1 minus 2. So that's 1 minus 3 minus 2, which is 1 minus 3 is minus 2, minus 2 minus 2 is minus 4. And that agrees with g of minus 1, and that agrees with the value on the right. So this is in fact a continuous function at minus 1. Cool. Now, for the rest of these problems, I'm still going to want to refer to that graph. So what I'm going to do is take off this page for just a minute. You can see the slightly painted over table I've got here. Now let's fold the graph over so you can see what the graph looks like. B says order h double prime of minus 2, minus 2, h double prime of 2, and h double prime of 10 from smallest to largest. How do we find these? Well, this one's interesting. H double prime of minus 2, that's in the region where h of x is just x squared plus 3x minus 2. So all we have to do is take two derivatives. So all we want here is x squared plus 3x minus 2 double prime evaluated at x equals minus 2. Well, that's first derivative of x squared is 2x, second derivative is 2 is a constant, and both of the other terms are 0. Right? Because the derivative of 3x is 3, the derivative of 3 is 0, and the derivative of negative 2 is just 0 to begin with. So this is just 2, which you could evaluate at x equals minus 2 if you want, but it's a boring thing to do because it's still just 2. So that one's 2. What's h double prime of 2? Well, that's the second derivative of the integral from 2 to x f of t dt. And the cool thing about a derivative of a thing like this is it doesn't care what that lower bound is. Why? Because we can move the lower bound anywhere we want. The integral from a definite place to another definite place, say an integral from 2 to 0, or an integral from 2 to 6, or whatever you have like that, is just a constant. So when you get its derivative, it vanishes. So all we care about is the upper bound. And then for that, we can use the Fundamental Theorem of Calculus. So this is just the derivative of... So first, this is just f of x by the Fundamental Theorem of Calculus, and then we're taking its derivative. So now we have to ask, what's the first derivative of x at... What's the first derivative of f of x at 2, and what's the first derivative of f of x at 10? Well... At 2, you can see the graph is sloped down, so it must be negative. At 10, you can see the graph is at a minimum. It's at a local minimum. And so the derivative must be 0. So h double prime of 2 is negative. H double prime of 10 is 0. H double prime of negative 2 is positive. So you can order them really easily. That's the second part of this problem. Let's look at the third part. Third part says, scroll this up so you can see it just enough. Evaluate the limit as x approaches 6, g of x plus 3 e to the 12 minus 2x over x squared minus 36. Well, what can we see here? The denominator is clearly 0. 6 squared is 36. 36 minus 36 is 0. How about the numerator? Well, g of x is the integral from 2 to 6 of x. We know that's 3. Sorry, we know that's negative 3. It's 3 down below the axis, so that's negative 3. So we have negative 3 plus 3 times e to the 0, which is also 3. So this is 0 over 0, which means this is a 0 over 0 indeterminate form. So what do we need to do? We can use L'Hopital's rule. Since this is a 0 over 0 indeterminate form, by L'Hopital's rule, this must be equal to the limit as x approaches 6 of the derivative of the numerator over the derivative of the denominator. So that's the limit as x approaches 6. I'll take a break here so you can see it clearly. My camera has a very bad habit of blowing out the contrast when I put my hand in the way. That's because my hand is kind of shiny. So I put it here. It thinks the world is brighter and turns the contrast up. Let's see. Let's try this again. So the good thing about, let's do the denominator first because it's easy. That becomes 12x. Great. The denominator is not 0. What's the numerator? Well, it's g prime of x plus derivative of this thing. Well, that's, here we have e to the 12 minus 2x, so that's 3 times e to the 12 times e to the minus 2x, right? That's what's that's a sum or difference up in the numerator just means you could have the multiplication of the two terms. These are just constants, so we don't care. The derivative of e to the minus 2x is just minus 2 e to the minus 2x. So the cool thing is this is something now we can plug into. So what are these things? Well, let's try evaluating this at 6 for a second, see what we get. G prime, well remember, G is defined as the integral from 2 to x of f of x. So the derivative is just f at that point. What's f of 6? 0. Great. So this is 0, my favorite thing to compute because it's easy. What's this? This is 3 e to the 12th times minus 2 times e to the minus 12 over 12 times 6, which is 72. So this is equal to, you notice this isn't going to be 0. This is not 0 over 0. We're done with indeterminate forms. Up here we've got e to the 12 times e to the minus 12, which is very easy. That's 1. That's e to the 12 divided by e to the 12, which I can do in my head. So we have minus 6 over 72. Well, remember we got 72 in the first place by saying it was 6 times 12, so that's minus 1/12. And we're done. You have to like a fundamental theorem of calculus problem where the answer turns out to be negative 1/12. That's just pleasant. Now, D is an interesting one. D says, evaluate. The integral from 1 to 7. 3h prime of 2x minus 4 plus 5. So how do we find h prime of 2x minus 5? Sorry, 2x minus 4, rather. Well, h prime in this area is just f of x. Ah, not quite. We have to be very, very, very careful. That 2x minus 4 is going to make us confused. It just made me confused because I'm tired. See, when we see 1 to 7, we think, great, we're in the region where h is just g. So I can use fundamental theorem of calculus to say h prime, but then this isn't h of x, this is h of 2x minus 4 dx, I should say. That 2x minus 4 is going to hurt our heads. Let's get rid of it with a u substitution. So let's say u is equal to 2x minus 4, so du is equal to twice dx, or rather, dx is equal to 1/2 du. When we make those substitutions, we get, and here's where things get tricky. 1 and 7 are x values. We're now changing to u. Remember, u is 2x minus 4. So if x is 1, twice x is 2, and 2x, so 2 minus 4 is negative 2. So this is integral from minus 2 to 7 times 2 is 14. 14 minus 4 is 10. So this is integral from minus 2 to 10. 3 times h prime of u plus 5 times 1/2 du. That 1/2's not going to bother us, so let's pull it out. Let's break up these terms now. That's an integral, that's 1/2, an integral from minus 2 to 10 times 3h prime of u du plus 1/2 integral from minus 2 to 10 of 5 du. And now you see why we had to be careful. I can't use the fundamental theorem of calculus here. H prime is not equal to f on this region yet. It's close to that, but between minus 2 and minus 1, h is still that quadratic function. So what I have to say is, this is the I have to break this up. I have to break this up into two intervals. One where h has the quadratic definition, one where h is just g. Because remember, our definition here is that as long as you're less than minus 1, you're still this quadratic here, h squared plus 3x minus 2. It's only at minus 1 you switch over to being g. So this is 1/2 an integral from minus 2 to minus 1, 3h prime of u du, plus an integral from minus 1 to 10, 3h prime of u du, plus, and now this one we can just do, 5/2 times u evaluated from minus 2 to 10. And now we're in good shape. Because now in this region we have 3/2 times an integral from minus 2 to minus 1 of x squared plus 3x minus 2 prime du, plus 3/2, just pulling out the constant again. And now here we can use the fundamental theorem of calculus. This is just the integral h prime, remember, is just f. So this is just the integral from minus 1 to 10 f of u du. And you might say, oh, but I didn't have an f of u, I had an f of x. The variable doesn't matter. F of u is the same as f of x is the same as f of kumquat. It doesn't matter what you put in there. It's the same thing. Plus finally here we have a nice easy one. 5/2, 10 minus negative 2, plugging in the numbers. So here we have 3/2 times the integral from minus 2 to minus 1, 2x plus 3 du. That's a nice easy polynomial to integrate. In fact, we could have just used the fundamental theorem of calculus, right? Because it's the integral of a derivative. It's just this fundamental theorem of calculus. It's just x squared plus 3x plus 2. We don't really need to do the integral or the derivative. Plus 3/2 times this integral. And how are we going to do that integral? Well, we already gave ourselves the answer. It's right here. It's the integral from minus 1 to 10 of f of u du. Well, that's 4 minus 3 plus 2. So 4 minus 3 is 1, plus 2 is 3. Times 3. Plus, here we have 5/2 times 12. Fine, that's 5 times 6 is 30. So this is 3/2 times, well, just our original function back. Although we can throw away the 2 if we want, because, again, the constant part doesn't really matter. It'll difference itself off anyway. Evaluated from minus 2 to minus 1, plus 9/2 plus 30. What is this? This is 3/2. Just plug in each one. Negative 1 squared is 1, minus 3, minus the quantity, 4 minus 6, plus, let's see, 69/2. That's 3/2 times. That's minus 2, so that's plus 2, so 3. Haha, that's 3. That's plus 2, plus 1 is 3, minus 3 is 0. Goes away. So our final answer is 69 halves. Better known to its friends as 34 and a half. Nice that we give a nice human answer at the end of the problem. Okay, last part of this problem. Part E, someone said, let y equals k of x be a particular solution. Be the particular solution of the differential equation dy dx equals x prime h prime of x times y minus 1 for x is less than negative 1. Find the particular solution y equals k of x. In terms of x. Given initial condition minus 2 comma 2. So we know that what this is saying is we know that if we have y equals k of x, we can plug it into this thing, and what we'll get, and we know that minus 2 comma 2 is a solution to this thing. And so if we plug it in, we'll get a reasonable answer. And just the initial condition here, somewhat unfortunately, it starts with x equals minus 2, so we start in that quadratic part, which is a little unfortunate. Okay. Let's see. Looking at the time, and we're coming up on the end of the show, and I haven't done even half of what I was hoping to do tonight. So what I'm going to do here is take, that said, there's still more interesting things to talk about. So let's take a 5-minute break. We'll come back and we'll keep going with the show. This is Nighttime Mathematics Radio. If you have any questions, feel free to tweet them on Twitter. For now, this is Nighttime Mathematics Radio. Back in 5. Once again, this is Nighttime Mathematics Radio. If you have any questions, feel free to tweet them in. I'll answer them live on the air. Welcome back, everybody. This is Nighttime Mathematics Radio. Let's take a look at that problem. The last problem asks this. It says, we want to find the solution to dy dx is equal to h prime of x, y minus 1. We're told this is true for x equals x is less than 1. And we're told to find the particular solution where, for k of x, where we're told it passes through minus 2, 2. Remember, what a particular solution to a differential equation is it's a solution that happens to satisfy it. It's not the general solution. It's not the only solution. There could be an infinitude of solutions, but this is one that works. That's all you're trying to find. And the reason is using some really clever bits of math. You can show that once you have a solution, you can really easily generalize it to many, many solutions, or in fact find all of them. So how do we solve this? Well, let's separate the two variables. Let's get the x's on one side and the y on the other. So we have 1 over y minus 1 dy dx is equal to h prime of x. Now let's integrate both sides against x. So this is the integral 1 over y minus 1 dy dx is equal to the integral of h prime of x dx. This has the easiest use substitution ever. Let's just integrate with y instead. So we say, so let's say y equals y of x, dy equals dy dx dx. So this whole thing is just dy. So that's the integral of dy over y minus 1. And this side, the integral of h prime of x is easy. That's just h of x. What's the integral of dy over y minus 1? Well, it's just the natural log of y minus 1. And now I'm going to carefully put that constant in. It's got to be on both sides, but we only need one constant. Both sides have a constant, so whatever. That's equal to h of x. And we're told one point this must pass through. This must pass through x equals minus 2, y equals 2. So the natural log of 2 minus 1 plus c is equal to h of negative 2. Remember, h of negative 2 is given just by that polynomial. So that's minus 2 squared plus 3 times negative 2 minus 2. Natural log of 2 minus 1 is just natural log of 1, which is 0. So the constant is equal to 4 minus 6 minus 2. So 4 minus 6 is minus 2, so the constant is equal to negative 4. So what that tells us is the natural log of y minus 1 minus 4 is equal to h of x. Or in fact is equal to, and we know what that is. That's because the solution only works for x less than minus 1, so we know this is in fact the quadratic. This is x squared plus 3x minus 2. So add the 4 to both sides. Natural log of y minus 1 is equal to x squared plus 3x plus 2. Take e to both sides. Y minus 1 is equal to e to the x squared plus 3x plus 2. Or y is equal to 1 plus e to the x squared plus 3x plus 2. And there's our particular solution. That's our k of x. And we're done. Okay, I'm probably going to save the images and kernels for tomorrow's show, because it's already 9:35. No one's asked any more questions on Twitter, so I think it's time to sign off. Well, everybody, it's been another great time to answer your questions. Keep asking questions at Night Math Radio on Twitter. If you like the channel, like and subscribe. Tomorrow we'll come back and talk about images and kernels and linear algebra. Or whatever other questions you might ask before then. This has been Nighttime Mathematics Radio. In a world where the math homework goes on and the classes have somehow stopped, Stay safe, everybody. Good night.